Now, in this lecture, we will discuss about the thermodynamic equilibrium. In the previous lecture, we discussed about the thermal equilibrium and how we can establish the concept of temperature from the thermal equilibrium. Thermal equilibrium means when two systems are in thermal equilibrium, then the temperature of the two systems are equal. When the two systems are separated by a diathermic wall, there will not be any net heat flow from one system to another if they are in thermal equilibrium. Now we will define another type of equilibrium, which is called thermodynamic equilibrium. Usually a system is said to be in thermodynamic equilibrium when conditions for mechanical, chemical and thermal equilibrium are satisfied. In this case, there's no tendency for any change of the state of the system or surrounding in its physical or chemical state. If a system is in thermal equilibrium, we have mentioned that there is no temperature difference between the system and surrounding or between the two systems. But in thermodynamic equilibrium, the condition for mechanical equilibrium must be satisfied, the condition for chemical equilibrium must be satisfied, and the condition for thermal equilibrium must be satisfied. That means in thermodynamic equilibrium, there will be no tendency for any change of the state of the system or surrounding any physical or chemical states. Now let's see what you meant by this mechanical equilibrium. Mechanical, you know that if there is a mechanical non-equilibrium conditions, there will be some unbalanced force at any part of the system. So if a system is in mechanical equilibrium, there will be no unbalanced force or torque acting on any part of the system or on the system as a whole. So mechanical equilibrium is the condition in which no unbalanced force or torque is acting on any part of the system or on the system as a whole. Now if you consider the thermal equilibrium that we have already discussed, there are no temperature difference between the parts of the system or between the system and its surrounding. So if there is no temperature difference between any part of the system or between the system and surrounding, then that system is called in thermal equilibrium. Now the third one is the chemical equilibrium. Here it is, there are no chemical reactions taking place within the system and no motion of any chemical constituents from one part of the system to another. So there are no chemical reactions taking place within the system and there is no motion of any chemical constituent from one part of the system to another part. So when these three equilibrium are satisfied by a system, then that system is said to be in thermodynamic equilibrium. When the conditions for mechanical, chemical and thermal equilibrium are satisfied by a system, then that system is called in thermodynamic equilibrium. Now if you consider a system and any change in force or temperature or chemical activity of the system in thermodynamic equilibrium leads it to a non-equilibrium state. Suppose if we change the sum of the external force, so if we change the sum of external force is changed, which will lead to finite unbalanced forces acting on the system. Force acting on the system. So these finite unbalanced forces will generate turbulence and which will set up waves in the system, so that condition for mechanical equilibrium is disturbed. So when there is a finite unbalanced force acting on any part of the system or as the system whole, some sort of turbulence will be generated and it will set up some waves in the system, or it may execute some sort of accelerated motions. These acceleration motions will, or the waves will set up a temperature difference within the system, or we can say that it will set up a non-uniform temperature distribution as well as finite difference of temperature between the system and surrounding. So now sudden change of force and temperature will lead to chemical reactions. So what we are saying is that if the sum of the total external force is changed, it will lead to finite unbalanced forces in the system, which will lead to make some turbulence within the system and which may lead to setup of a wave or some sort of accelerated motions within the system or the system as a whole. So which will generate or which will lead to non-uniform temperature distribution as well as finite difference of temperature between the system and surrounding. A sudden change of the force and temperature of the system will lead to chemical reactions, so that it will upset the conditions for the thermodynamic equilibrium. But if we are considering that the external forces are varied only slightly, so that unbalanced force, this one, is infinitesimal, then it will not generate any turbulence or waves or any temperature difference within the system and any chemical reaction within the system. Then the system will be in thermodynamic equilibrium, and due to this unbalanced force, there will be very little infinitesimal temperature change, or the system may change from one state to another. Then that process is called quasi-static. So this quasi-static process is a very important concept in the case of thermodynamics. So What a quasi-static process is that if the external forces are varied only slightly, so that unbalanced forces infinitesimal, and the system is always in thermodynamic equilibrium. So during a quasi-static process, the system at any instant is infinitesimally close to the state of thermodynamic equilibrium. So quasi-static process is an idealized conception, and rigorous conditions mandated by it can hardly be satisfied, yet by making the process slow and proceed gradually step by step, it may be made as nearly quasi-static as possible. So quasi-static process is a process which proceeds gradually or infinitesimally slowly, slow process in which during the entire process of the system the system is always in a state of, or nearly in a state of thermodynamic equilibrium. So quasi-static processes are the processes in which the system is always in the thermodynamic equilibrium during that process. So I told you that it is an ideal concept, as well as there are rigorous conditions mandated by it, and it can hardly be satisfied, but by making the process infinitesimally slow, we can make the processes nearly equal to quasi-static as possible. So ideally what quasi-static process is that during that process the system is always in a state of thermodynamic equilibrium, or nearly in the state of thermodynamic equilibrium. So in the further discussion of thermodynamics, we will consider the processes taking place are quasi-static. Now we know that in order to characterize a system, the state of the system is represented by the thermodynamic variables. Usually we denote it by x and y. These thermodynamic variables defining a thermodynamic system can be classified into two: extensive variables and intensive variables. The extensive variable means the variables which are proportional to the mass of the system, or we can say that it depends on number of moles present in the system, or the amount of substance present in the system. Examples for the extensive variables are volume, internal energy, etc. are extensive variable. That means they depends on the number of moles present or the amount of the substance or which are proportional to the mass of the system. Now if you consider the intensity variables, the intensity variables are independent of mass, or they are independent of number of moles present or the amount of substance. So the thermodynamic variables which are independent of the amount of the substance present in the system or independent of the number of moles present in the system are called the intensity variables. Example, pressure, temperature, etc. are intensity variables. So these variables are interconnected by the equation of state. We can represent their interrelationship in a quasi-static process by curves or diagrams drawn with the help of a device called the indicator diagram. So the interrelationship between the thermodynamic variables in a quasi-static process can be represented by curves, and that curves are called or representation, graphical representation of the interrelationship between the thermodynamic variables are called indicator diagram. You may be familiar with the pressure volume diagram, the PV diagram, the TS diagram, etc. So these are examples for the indicator diagram. In this chapter we will consider the PV diagram and TS diagram of different processes. So the interrelationship between the thermodynamic variables x and y in a quasi-static process can be represented graphically, and that graphical representations are called indicator diagram. So that's all about the thermodynamic equilibrium and indicator diagram. Now we will go into the quasi-static processes in detail. That is, we need to calculate the work done in a quasi-static process and all those things that we will discuss in the next lecture. Thank you.